These are the answers to homework 4F. Here are the definitions I'd like you to know. Now let's go to the questions. Number 1, the reaction 2NO plus F2 yields 2ONF occurs via the given two-step mechanism. Deduce the rate equation that agrees with this mechanism. Rate law can be determined from a mechanism by looking at the slowest step in the mechanism, looking at the reactants in the slowest step, and then raising the reactants to their coefficient as a power. Therefore, the rate of this reaction is going to be proportional to the concentration of NO to the first power and F2 to the first power. So the rate law will equal K, in this case K1 because it comes from the first step, but you could just write it as K, multiplied by the concentration of NO to the first, F2 to the first. Number 2, assume that the reaction 5Br minus plus BrO3 minus plus 6H positives yields 3Br2 plus H2O proceeds by the following mechanism. Deduce the rate law that agrees with this mechanism. Once again, we look for the slowest step in the mechanism, which is step 2. The rate of the reaction is going to be proportional to the concentration of the reactants in the slowest step. So the rate will be proportional to the concentration of bromide to the first power multiplied by the concentration of H2BrO3 positive to the first power. So the rate will equal the specific rate constant for that second step, K2, multiplied by Br minus to the first, H2BrO3 positive to the first. The bromide ion is a reactant in the overall reaction, but H2BrO3 positive is not. That must be substituted out. And that can be substituted out only from an equilibrium step, which is step 1. If we write the equilibrium constant expression for step 1, in the numerator is our H2BrO3 positive. We want to solve for that so we can substitute it back into the rate law above. So solving for H2BrO3 positive, H2BrO3 positive will equal K1 multiplied by the concentration of H plus squared multiplied by the concentration of BrO3 minus. Substituting that into the rate law, the rate of the reaction will therefore equal K2 multiplied by the concentration of Br minus multiplied by K1 multiplied by the concentration of H plus squared multiplied by the concentration of BrO3 minus. Combining the constants into 1, the rate law will be rate equals K times Br minus to the first, H plus to the second, BrO3 minus to the first. Number 3, what is the physical interpretation of the activation energy? The activation energy is the minimum energy needed by the reacting molecules for an effective collision. Second, why should it have any bearing on the rate of a reaction? And that's because the higher the activation energy, that means the smaller the percentage of effective collisions you're going to have, so the reaction rate's going to be slower. At any given temperature, molecules have a wide range of kinetic energies. The only molecules that can have effective collisions are the ones who have kinetic energy greater than the activation energy. So if this is the activation energy for a particular reaction, these are the only molecules, about 1/3 of them, that have enough energy that when they collide, they can actually cause a reaction to take place. If the activation energy were a higher value, then that means you have a lesser percentage, maybe 15 to 20% now of the molecules that will actually have enough energy to react when they collide. And because less collisions are now being effective, that means the reaction will go slower the higher the activation energy. Number 4, if you knew the activation energy for the forward and reverse reactions, how could you use them to calculate delta H naught and illustrate with a diagram? So I'm going to draw an energy profile for a reaction, putting the reactant energy content at the left side and the energy content of the products at the right side. A hump in the middle represents the required activation energy for the reaction. The red arrow represents the activation energy for the forward reaction. The blue arrow represents the activation energy for the reverse reaction if you just read the reaction profile from right to left. The difference between the energy state of the reactants and products is the enthalpy change of the reaction. That's delta H, and that's what they're asking to figure out. How can we get that green arrow? Well, that's going to be the red arrow minus the blue arrow. So therefore, the activation energy for the forward reaction minus the activation energy for the reverse reaction will equal the enthalpy change for the forward reaction. Number 5, the fraction of molecules that have the sufficient energy to cross the activation energy barrier, E sub A, can be increased by either 1, making the molecules more energetic, or 2 by lowering the barrier. So question 5a, what are you doing when you raise the temperature? So when you increase the temperature, you're making all of the molecules more energetic. That will cause the reaction rate to be faster because a higher percentage of them now will have the activation energy. What potential disadvantages are there in this method? Well, if you actually increase the temperature, you're not only increasing the rate of the forward reaction, but you're actually also increasing the rate of the reverse reaction. B, what are you doing when you add a catalyst? So when a catalyst is added, what's happening is you're lowering the activation energy barrier. And what does the catalyst do to make this possible? It provides a different pathway that allows less energetic collisions to be successful. And physically, the way it does it is a catalyst usually bonds to one of the reactants. It bends the molecule or the reactant slightly to cause the bonds to be stressed so that a lesser strength collision will be required to break that bond. Number 6, it is often said that near room temperature, a reaction rate doubles if the temperature is increased by 10 degrees Celsius, or 10 Celsius degrees. Calculate the activation energy of a reaction whose rate exactly doubles between 27 degrees and 37 degrees. So a couple things you have to understand in this particular problem here. If we have a particular chemical reaction where let's say A goes to B, and let's say the rate law is rate equals K times concentration of A. If I just plug in some pretend numbers, let's say our specific rate constant is 1 and the molarity of A is 1, then when you go 1 times 1, that means the rate of the reaction at whatever temperature this is 1. Now, if we raise the temperature by 10 degrees, the problem is said the rate doubles. So if we raise the temperature by 10 degrees, that's going to cause the rate to be doubled from 1 to 2. The concentration of A is not changing. So what has to be true about the specific rate constant when the rate doubles? Well, if you can figure this out, the question mark has to be 2. That means if the rate doubles, the specific rate constant must double as well. So that was an important consideration to even start problem number 6. If the reaction rate doubles with constant molarities, that means K has to double. So if we're trying to calculate the activation energy, we can do it from an Arrhenius activation energy plot, but we would need to know 2 different specific rate constants at 2 different temperatures, and we can kind of make those up. Because if we actually have the Arrhenius equation, natural log of K equals negative E sub A over R multiplied by 1 over T plus natural log of A, then a graph of natural log of K versus 1 over T will give us a line, and the slope will allow us to calculate the activation energy because the slope is negative E sub A over R. So what are we going to make up? I've got here, first line is temperature, second line is specific rate constant. So what if I have a temperature of, let's say, 300 degrees, which is 27 degrees Celsius? If I increase the temperature by 10, so it goes from 300 to 310, they've told us in the problem the rate has to double, and we've just deduced that if the rate doubles, that's because the specific rate constant doubles. I don't know what the numbers specifically are, but I can make them up 1 and 2 because that's doubling. They might be 0.003 and 0.006, but as long as I understand they double, I can still calculate the activation energy. Now, I'm going to need to make a graph of the natural log of K versus the reciprocal of the temperatures. So let me calculate what those are so I can actually graph them. The reciprocal of the temperatures I have here are 0.003333 and 0.003226. And the natural log of each of the specific rate constants are 0 and then 0.693. So on Excel, I'm going to make a graph of these 2 points. You can see the 2 points on the graph. And when I have it display the equation shows y equals negative 6,446.3x plus 21.488. In that equation, y stands for natural log of K. Negative E sub A over R is your slope. And so negative E sub A over R equals the negative 6,446.3. The x is 1 over t, and the 21.488 is the natural log of A. But the key to this, the only important part, is the slope, because the slope is negative E sub A over R. If I solve for E sub A by moving the negative sign and the R to the other side, my activation energy will be negative, the universal gas constant, multiplied by the slope from Excel. The universal gas constant, 8.314 joules per Kelvin. The slope has to have units of Kelvin because rise over run is difference in y's over difference in x's Natural logs have no units on the y-axis, but the x-axis is 1 over Kelvin. So 1 over Kelvin makes the units of the slope Kelvin. Kelvins cancel out. The answer comes out in joules. The two negative signs cancel out. It's a positive answer. And therefore, the activation energy for this reaction has to be 53,600 joules. Number 7, the rate constant for the decomposition of N2O5 in carbon tetrachloride is 6.2 times 10 to the minus 4th seconds to the minus 1 at 45 degrees Celsius. Calculate the rate constant at 100 degrees Celsius if the activation energy is 103 kilojoules. So here's another problem. It's relating specific rate constants, temperatures, and activation energy. The only difference is the variable we're solving for is not the activation energy. They've given that to us. We're trying to find the specific rate constant at one of the particular temperatures, at this case 100 degrees. So starting with this expression here, which is the Arrhenius activation energy equation, in this equation, the slope is negative E sub A over R. And what is slope? It's difference in y's over difference in x's. So negative E sub A over R will equal the difference in the natural log of k's, so natural log of K2 minus natural log of K1, over the reciprocal of the temperatures, 1 over T2 minus 1 over T1. And if I can figure out that slope is going to equal E sub A over negative R. So here's how we do it. I plug in E sub A over R, which switched to joules would be 103,000 joules, divided by negative 8.314 joules per Kelvin. That actually equals my slope, right? And what does the slope equal? Difference in y's over difference in x's. So the difference in y's will be the natural log of K2 minus the natural log of K1. So I'm going to pick my second point, the K2, for the higher temperature of 100, and K1 is going to be for the temperature of 45. So the specific rate constant 45 degrees was 6.2 times 10 to the minus 4th. So I'm going to do the natural log of 6.2 times 10 to the minus 4th. My higher temperature, once again, is the 100 degrees Celsius. So I'm going to go 1 over 373.2 Kelvin, which is the Kelvin equivalent of 100 degrees Celsius. And then minus 1 over 318.2 Kelvin, which is the equivalent of 45 degrees Celsius. And now I have a giant equation where I just have to solve for the individual variable, K2. So the left side of the equation can be calculated. The denominator can be calculated. If I do those, the left side becomes negative 12,389 Kelvin, and the denominator becomes negative 0.000463 Kelvin to the minus 1. If I move the denominator of the right side over to the left side and multiply it out, the units cancel out, and I just get 5.736 equals natural log of K2 minus the natural log of 6.2 times 10 to the minus 4th. I just have to add the natural log of 6.2 times 10 to the minus 4th to both sides of the equation, and I'm going to get the natural log of K2, which turns out to be negative 1.650. Taking the anti-log, or raising both sides of this equation to E as a base, I can calculate my value for K2, and the K2 value, the specific rate constant at 100 degrees, turns out to be 0.19.